controlled side effect. Okay, if suppose I have a production L gives E, instead of giving L dot val is equal to E dot val, so this is the production and this is the STD. Okay, instead of doing this, what I can do is print the value of E dot val. Okay, so whenever you want some, this is this controlled side effect. So whenever E is getting reduced to L, we can perform some of the implementation codes. This you have done in YAC, right? So what you have done, E gives E plus T. There you have done dollar is equal to $1 plus $3. Okay, so what is this? This is a implementation code. So what you're doing, whenever E plus T is getting reduced to E, with that, you have also combined this, because YAC is a parser, okay, which is a syntax analyzer, which implements the syntax analyzer. So when you're writing this implementation code, this doesn't come in syntax analyzer. So what it is doing, it is combining some of the features of semantic analyzer with this, right, in YAC, so that you are controlling the side effect which is given by this particular production. As a side effect, what you're doing, you are embedding the implementation code. That is nothing but your syntax directed translation, you can say. That means you are implementing something when a production is given. So this is very useful when you are, for declaration kind of statements. So you are manipulating the symbol table, suppose. So you have int a. Okay, now you have to relate the type of the variable to a. What you should do? You have to go to a's entry in the symbol table, and you have to relate this integer type with the entry, because that is the attribute which is given for this particular token ID, right? So this will point to a symbol table entry for A, and then the attribute value I have to enter as integer. Okay, so what is the grammar which we are going to use it for? I have briefly given you this particular grammar when I was explaining about the inherited attribute, right? So D gives TL. So this is a declaration which is made up of type and the variable. Okay, so if you have to write the tree for this, T and L can further give ID, and T can give int or float or something like that. So this will have int and this will have ID. Okay, so you have to bring this int to ID, this level, and what you're supposed to do, you cannot get the value back to D. That is not required here. Okay, what will you do if you get the value at D? It is not an evaluation like arithmetic expression, right? So your main task here in the declaration statement is whenever you get this ID and the integer, at that particular node, I have to add an entry for this ID for the type of this variable. Okay, so I have to execute something like add entry or add type or something like that. Some code embedded should be there with respect to D gives TL or L gives ID, wherein I get the type of the variable and also ID with this. Okay, so I have to call some method which will put this type onto the symbol table. So in those cases, we require this control side effect. Okay, we require this. As a side effect for this particular production, I will call some method, okay, which will make an entry in the symbol table for me. Okay, that is controlled side effect. That is the main use of the STD when you combine it with the syntax analyzer. Okay, so I will discuss this this thing with a complete grammar for this. You understood what is controlled side effect? If you have any questions, I will take. Otherwise, after the explanation of the whole grammar, we can discuss, no problem. Okay, and these are the rules, semantic rules. So the whole grammar being, because I need to have both int A kind of declaration and also I should have ABC kind of declaration. Okay, so my complete grammar should include both of them. You can also try writing the grammar if you want to try. So this is a semicolon, then T gives int. I will just give it for integer and float. Okay, like that you can have character, double, all the primary data types. Then you have fourth as L. L gives L comma ID to have multiple variables in the same declaration line. Then you have L gives ID. Okay, these are the productions for a declaration statement. Okay. Now, what should be the rule? How will you write the rule? Anybody can help me with this? How will you write the rules? You take type as the synthesized attribute. Okay, and inherited as the inherited attribute. Dot type and dot inherited as. Okay. Tell me, who will tell me? At this particular production, what should be the rule?
Ma'am, L will inherit T's value, right?
So how should I write?
So L dot inherited is equal to T dot val.
T dot, I will take the type. Value will represent value. So type, we are discussing about the type of the variable, right? So I will take it as type. Okay. Here, so you will get the tree as T gives int. What should be the rule for this? This is simple, no? This is T dot type. You are defining the type here as int or integer. Okay, T dot type as float. Right? So you are taking integer. So this is a synthesized attribute. So the same type you are inheriting to L. Because if you write D as T L, type will be there here. So you have to inherit that to the variable. Here you tell me. Okay, we'll write this later. We'll take an example and then we will write, so that it will be easy for you to understand whether I have to write the inherited or the synthesized. So let us take this example, int a comma b comma c. So it is nothing but int id1, id2 and id3, because we don't have abc here. We, in terms of id, we'll have to write. So it is int id1, id2 and id3, which I'm going to consider, which can be generated from this grammar. Okay, isn't it? Now, this 1, 2, 3 refers to different, the token is ID only, but 1, 2, 3 will differentiate this with each other. Okay, so this ID1 should refer to the entry for A, ID2 should refer to the entry for B, and ID3 should refer to the entry for C, which is done in the lexical analyzer. Int is separately taken, A separately taken, B separately taken, C is separately taken, and we have constructed the symbol table. Okay, we have the pointers for ABC, but we haven't mapped this int with ABC, that is remaining. Okay, using the grammar, we are going to do that. Okay, so now how will you write the tree for this? You start with the D, then you have, or if you write it L, and this is semicolon. Even if you don't consider this, it's fine. This is L. Then T is int. Then L is what? L is what?
L comma ID.
L comma ID. Okay, then this L should give L comma ID. Then because we have int ABC, right? So L should give L comma no, two IDs are done. So it has to be L gives ID. Okay, so if you take ID 1, 2, and 3. So if you pass, if you traverse this tree, you should get ID 1, comma ID 2, comma ID 3, and a semicolon. Okay. Now, can you write the dependency graph here? This how it will evaluate. You get this int defined, right? Then you take this up. I have to use t gives int. What is the semantic rule? T dot type is equal to int. So t dot type is equal to int. Okay. Now ID1, ID1, ID2, ID3. What they refer to? They refer to the entries of the symbol table. So I will make them as 1, 2, 3 because it is already existing. Okay, these are the entry for A, this is entry for B, and this is entry for C, the symbol table entry for this. So we have the pointers at this particular node. Now, if I have to enter the type for ABC, I have to get the type to this level. L gives ID. Okay. At L, I can have both the pointer and also the type. Then only I can do the entry in the symbol table. Correct? Agree with me? Right? Otherwise, I can't do. Even if I have only the type, I can't do the entry. Even if I have only the pointer, I can't do the entry because I have to associate them. Okay. Now, how will I do? I will say this is the fourth one. Okay. So I got this. You can say this is fourth and this is fifth. That is also fine. I refer to this as the fourth node. Okay. This is fourth. Now I inherit this to L because L and inherit is equal to T dot type. So I inherit this to L. Okay, wherein it is inherited attribute. Now at this L, what should I do? This L, what should I do? I have the type with me at L inherited. I have the type. Now I have an ID also here. I have L also, but I have an ID also. I can make an entry for this ID, right? So what can I do? I will make an entry for 6. 6 is the entry with the type for this ID 3. So how will I do? I will say here that you add type of ID dot entry with what? With, where is my type? In which attribute?
L dot inherited.
Correct. So I have to add the type. So I will write the type first. Let me write the type first. L dot inherited with the ID dot entry. Okay. So I will add that. Now what about these two? I have to inherit them, right? Once I inherit them, I have this rule. So I need to inherit also from L to L. From this L to this L, I have to inherit the type. So this is also inherited attribute. So for this particular production, I have 2 rules. One is for adding the type. The other one is, if you take this one as L1, so L1 dot inherited is equal to L dot inherited. So you are inheriting from this L to this L, and also you are adding the type for this ID. Okay, if you see here, I can also add the type for this ID too, because I have the type and the child has the entry pointer. So I will do at 8, I will do the entry. Okay, now at this particular node, okay, I have, what is the production? L gives L comma ID, L gives L comma ID. So I'm inheriting the value to this L. Okay, this is 9. Now at L gives ID, I have this production now. How do I evaluate the value at L? Okay, so now what is the point here? I have to add an entry to the symbol table with the type for that particular variable. Okay, at L gives ID, I need not define any value, right? Because I already have the type with me. I will call add type. This is a controlled side effect for this particular grammar. So L dot inherited, I have the value type, okay, then ID dot entry. This is for this production. You have only one rule which is associated with L gives ID because I am inheriting from L. This L is the type at this particular node is getting inherited to this L, wherein I have the pointer and the child and I have the type, so I can associate this. This is the entry for A. Okay, now remember here 6, 8 and 10 are dummy nodes. Okay, they are just showing you that the entry is done because automatically that is done. That is related to the same production, which we have already highlighted with 5, 7 and 9 for the inherited attribute. Okay, these are dummy nodes which I have shown you. So the order of evaluation is like this only. Okay, so you can point the nodes in the beginning, which is coming from the symbol table. So 1, 2, 3, 4, 5, 7, 9, you can say. Or if you want to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You cannot change the order here in this case. Any doubts? Understood?
What about getting the value at D?
At which?
D root number.
No, that's what I'm telling you. No, we won't get the value back because it's not arithmetic expression grammar. This is the grammar which is used for matching the type with the variable. Only for the arithmetic expression you are getting the value at the root, not for all.
Okay, got it.
Got it? Yeah. So here, if you see, it is having left recursion. That means you can think that it's a bottom of parser grammar. Okay, but the problem is here, even though it is having a left recursion, bottom up parser, the main requirement of this grammar is to associate the type with the attribute, the variable. Okay, only for the arithmetic expression you can see and decide on the attribute values. Otherwise, I always tell you to take a string which can be generated from the grammar, write down the parse tree. You will understand whether to inherit or to take it from the child, the values, then write the rules. Don't simply mug up the rules. You will not understand. If you do some mistake, it is gone. Okay? Follow this method. Okay? For arithmetic expressions, you can straight away looking at the grammar, you can say, if the operators and the operands are not on the same subpart of the tree, you can decide there will be some inherited attributes at the nodes. Okay, if you get both of them, the operands and the operators on the same level and same subpart of the tree, then it is obviously the synthesized attributes. Okay, any doubts you have? So Furqan is absent today. Okay. Then we go for the applications of.
I have one doubt. In
Huh.
this tree, there's no synthesized attribute only, right?
It's there, no T dot type is a synthesized attribute, right? Type.
Okay. But
So inherited attributes, always we say dot inherit, inh. It refers to the inherited attributes. Otherwise, no. It should be val or type or something like that. Or syn, a synthesized attribute. So if you haven't done that homework, I